Hello everyone, welcome back to the second part of this lecture on mechanistic modeling. In the second part we're going to especially focus on mechanistic modeling of chromatography. We're going to take a detailed look at the mathematical models that describe chromatography on a basic level. And then we are also going to look at what different models exist and how these models are used. We want to start with a short introduction on why we need mechanistic model for chromatography. And for this, I brought you this chromatogram on the right side of the screen, where you can see the typical time series data of a elution process. In blue, you can see the absorption in the UV spectrometer. At the end of the chromatography system, I can see that while increasing concentration B, our protein is eluting. We can see this nice peak. And you can see that later on there are some smaller peaks, and initially at around time point zero there's a larger peak. So this is a typical chromatogram, and here we can see the breakthrough of our protein and also the elution of our protein. And now we want to have mechanistic models that can help us understand better the separation behavior of different proteins in chromatography. We want to predict the time points and the elution conditions of our breakthrough, and we want to use these models to support the process digitalization and also optimization. So the goal could be that this experiment here taking 60 milliliters is done with a lower volume. Buffers are expensive, then they're also time consuming, so reducing this time could increase the productivity. Maybe we also want to learn more about the adsorption desorption behavior of our system. So we are trying to use models to be able to learn something about a model to better understand the system. And then also models in chromatography are important if we want to transfer our knowledge, right? So if we want to upscale this process, work in larger volumes, models build a good basis for upscaling and as a good starting point. So what is happening inside our chromatography column? I again have this nice graphic on the right side that you already saw in the first lecture, and we're going to work through the important parts of what is happening inside the chromatography column step by step. So first, our molecule enters the column. This you can see on the left, pointed by this arrow, and is then transported by the flowing mobile phase through or in between these particles or beads inside the column if we have a packed bed column. You can see this in the first zoomed stage, or here in the laser pointer. So all this green marked space between these particles is the fluid phase, and the fluid phase is flowing from top to bottom and is thereby also taking these molecules with it. This is what we call convection. This is the main driving force of the molecules through the column from the beginning to the end. At the same time, these molecules are not only using due to the fluid flowing, but also due to dispersion. So this could mean the molecules are moving a little bit back, moving a little bit forward, moving a little bit in a radial direction. So this is due to the actual dispersion. The molecules can then also, if they're small enough, move into the pores if we have porous particles. For this, the particle has to pass this liquid film around the particle beads and can then diffuse into the particles. And inside of the particles, the molecules can then, well, have the pore diffusion. They can move around. They do move around, but they can also interact with the surface of our particles and can come to adsorption, which means that the molecule is binding to the surface. As you can see here in this last zoom stage, the molecule is binding to these ligands on the surface of our adsorber. And then the last stage that is sometimes looked into is the movement of the particles on the surface, right? So particles bound on the surface might interact with other particles bound on the surface. They might move around, change their binding spot. They might have a repulsion so that there's always some space between them. But these are all effects that impact how long a molecule is on the chromatography column. And based on the different behavior of different molecules, we can achieve a separation. So this is the basic principle of chromatography. So from this explanation of how the molecule is moving through the column, we can already simplify the chromatography into two models or two systems that we then will look at in detail each. So we have a transport model and we're going to have an absorption model, and together they build a full model of the chromatography of the chromatography system that is able to predict the breakthrough, dilution, and a peak shape. The transport model is going to focus on how the molecules move through the system, while the adsorption model is going to focus on all the interaction of the molecule with the stationary phase, so the surface of the molecule. So the molecule moving through the column, moving into the particles, moving around inside the particles, this is all the transport model. The adsorption model, that is going to focus on how the molecules interact with the surface of the stationary phase. So let's look at the transport part of this model, the transportation. Going back to the equation and having these molecules move through the column, we have the convection, as I said, and we also have dispersion. So we have convection, we have axial dispersion, and then we have exchange with the stationary phase, which just means molecules moving into the particles through this film barrier on the outside of the particles. And we can explain or describe this mathematically with this differential equation shown right here. We have the change of our concentration over the time. So this is the accumulation. So this term describes the concentration at each time point inside of our column. So if we ask this differential equation, if we solve it, we get the amount, or in this case, the concentration of molecules. So this describes the accumulation of molecules inside our column. And this is defined by the convection term in green. So we take into account v being the interstitial velocity, so the speed of the convection, and we also take into account the axial dispersion, which takes the axial dispersion coefficient and the concentration over z, while z being the resolution across the length of the column. And then we have this equation at the end that describes the exchange with the stationary phase. Right? So delta Q over the time is the concentration in the stationary phase over the time, and parameter epsilon is the column porosity. So the amount of or the ratio between the green space in this graphic and the white particle spaces. So the room that the molecules can travel through without having to go into the pores or into the particles. If we zoom in another level, as I said before, the particles or the molecules, if they are small enough, can go into the pores of the particles. And then we have equations that describe everything that's happening inside these particles. And here first we start off with the accumulation inside the particle. This looks quite similar to the accumulation outside the particles in the fluid phase. Here we have the concentration of the molecule inside the particles over the time, described by pore diffusion. So this is movement of the pores inside of the particles, and then a possible adsorption term, right? So anything of all the molecules, or if the molecules are interacting with the surface, they're leaving the fluid phase inside of the particles and would therefore be gone from the fluid inside the particles. For this transport model, there are now different approaches how to solve it, mostly depending on how complex we want the system to be, right? So depending on the physical realism, on the parameter demand, on the computational effort, and the intended application, we can apply different models. And today we are going to work through the four most basic or most principal models. We're going to talk about the equilibrium dispersive model, which is the simplest model for transport and chromatography. We're going to walk through the lump rate model with and without pores, and then finally we're going to come to the general rate model, which is the most complicated or the most general model available for chromatography. And as you all can see indicated by this arrow, the models get more complex along the way. They take into account more parameters and make different assumptions. So if we talk about the equilibrium dispersive model, we have to talk about the assumptions we make. In this model, we make the assumption that there's a local equilibrium between phases, there's no explicit mass transfer resistance, so we are not computing any mass transfer between the um, fluid phase outside of the particles moving inside the particles, and that all the band broadening is represented by axial dispersion. The advantages of this model are that it's super simple and that we have a low parameter demand. And on the right, you can see the equation that fully describes this equilibrium dispersive model. And this equation looks or is exactly the equation you've already seen for the transportation phenomena. Again, in green, we have convection. In blue, we have axial dispersion. And the purple part is describing the adsorption in this case, so delta Q, Q being the stationary phase over T. And here we assume that there's an instant equilibrium, so there's no kinetic resolution to our adsorption process, but all the adsorption effects are captured inside this delta Q over delta T. And this already brings us to the limitation of the system. We are limited in the kinetic realism of our system. However, the advantage, as already said, is that this is a super simple model and we have a low parameter demand, right? The parameters we need are the axial dispersion. We need this velocity that is already quite easily determinable. We have to know the porosity of our column, and then there's some form of equation that describes the adsorption. Next, if we want to make it a little bit more complicated, a little bit more detailed, we have the lumped rate model without pores. The name is already giving away what this main assumption is in this model, namely being that we are not looking at pores. However, we want to take into account some transport effects, and these transport effects are combined together into one effective parameter, here being this K. So this is a little bit more realistic than the equilibrium dispersive model because it takes into account that in reality the molecules have to move through this film barrier around the particles. They move around inside the particles and it takes some time for the absorption to happen. So they have a layer of complexity added on top. The limitation is being this is still a reduced physical resolution, right? So we're still not capturing the full process. The equation changes a little bit, as noted before. So now we don't assume instant equilibrium, but we have some factor here that takes into account all these real processes that are happening, but they are lumped into one parameter, which is also why the model is called lumped rate model. The next level of complexity would then be the lumped rate model with pores. So here we now take into account effects like pore diffusion and adsorption that are happening, and they're not anymore thrown together into one parameter, but are happening in different parameters. This is also the first stage where we actually distinguish between a liquid concentration in the pores and a solid phase. So before we had the concentration inside of the fluid phase or the mobile phase and the solid phase Q, but now the lumped rate model with pores takes into account the liquid concentration or the concentration of the molecules inside the pore liquid, here called Cp. We have a change to the differential equation again. We have this transportation factor K, right? This is from the mobile phase outside again, this equation. Here we have the change that is going inside of our pores. And then we have now one full equation describing what is happening inside of our pores. Again, this transport equation telling us what is happening, or this equation at the end that describes the effect of the adsorption or the binding processes, so the movement to the stationary phase Q. And then again, the stationary phase Q is again described as in the lumped rate model without pores. So one key takeaway from this lumped rate model with pores is that we have an additional step between the mobile phase and the stationary phase, which is the pore phase Cp. And then as the most complex model that we're going to look into in this lecture, we have the general rate model. And a general rate model now explicitly includes all these effects that we mentioned before. It includes actual convection, it takes into account axial dispersion, it takes into account film mass transfer effects, the diffusion inside the particles, and also adsorption desorption effect. So as you can already see, we have a small modifier to our general mobile phase equation. and this is due to the mass transfer. We have Kf, which is a mass transfer parameter, and we have this value 3, which comes from the particles being radial or spheres. And then we have a more complex equation describing all the effects happening inside of our pores. So we have the concentration of a molecule inside the pores over the time dependent on the diffusion coefficient of our inside our particles. And here you see a lot of r squared. So now this takes into account the spherical shape of our particles. So that it obviously takes some time for the molecules to diffuse into the particle, correct? So that is taken into account here. So here the geometry is taken into account, and then at the end we have the equation again that then makes a transfer between the fluid phase inside the particles to the actual surface, the stationary phase. So this generate model captures everything that you can see down here on the bottom left in this graphic that we have already talked through sometimes. Okay, so we have now looked into some different transportation models that exist and what the upsides and downsides are, the different complexity levels. However, what all of these models are missing, or what I always see described as delta Q over delta T, so the stationary phase concentration over time, this is described by the adsorption model. So the adsorption model determines the equilibrium behavior, the adsorption model determines the saturation of the surface, this determines how the competition between the components is taken into account, and therefore also is an essential part if you actually want to model what is happening inside our model or inside our chromatography column. So we are free to combine different transportation models with different absorption models. So next we're going to look at different absorption models, what exists and what you might already know, what we're going to learn about today. You might already know the Langmuir model. This is the most extensively studied model, and the Langmuir model is a really simple model that describes how the concentration in the fluid phase and the stationary phase behave. The Langmuir model makes some important key assumptions. The first being that there is only a finite number of binding sites. So as you can see in the graphic on the right, there's only a fixed number of binding sites. So it's not infinite, so not infinite, it's not an infinite number of molecules can bind, but just a finite number of molecules can bind. The adsorption is reversible, so the molecule binding to the surface is not bound forever, but can be desorbed as well. In Langmuir, we assume that there's no interaction between the bound molecules, so this molecule does not at all impact another molecule binding directly to the left, even if in this graphic it might look as it were occupying. The Langmuir model assumes that every binding spot is equal and that the molecules do not interact with each other, do not prohibit other molecules from binding besides them. So the Langmuir equation, you probably might know, is already Q. So this is the bound concentration. The concentration in the stationary phase is determined by the maximum concentration bound to the stationary phase, multiplied this factor K, and the concentration, this is in the liquid phase, over 1 plus the factor K times the concentration in the liquid phase. You probably also know this saturation graph on the bottom right. If you increase the concentration in your fluid phase, you also will see an increased concentration of the molecules bound in the stationary phase up to a Qmax. So this is when the complete surfaces or all the binding spots on the surface are saturated. So this is the concentration. Even if you increase the concentration in the fluid, the concentration on the stationary phase will not increase further. All right, as you might imagine, these assumptions that I just showed are a lot of assumptions, and they leave out some real important physical aspects. So the first step is to um, introduce the multi-component Langmuir. So the initial Langmuir equation that I showed you only takes into account one molecule type. However, in chromatography, if we want to separate different molecule types, we need to have an adsorption system that allows us to have different molecule types. So this is where multi-component Langmuir comes into account. We again have some important assumptions, namely being that the binding of one component affects the other. This means that these components, these different components, are competing for the same binding sites. So if all the binding sites are occupied by one molecule type, let's say A, and B wants to bind, it has to remove A from the binding spots. So there's still a fixed number, a maximum amount of binding spots, and these two components or multiple components compete for the same binding sites. And this is typically used for mixed feeds, right, or competitive systems. You can see the Langmuir kinetic or the Langmuir equation adjusted here in a differential form. So it's the change of the concentration bound to the surface of a molecule type I over the time. And here we have this the binding factor, we have the concentration in the fluid phase of our molecules, Qmax, that is the Qmax for all the molecules, and then this term that takes into account the different molecule types. And here this back part that takes into account the concentration of the concentration of the molecule type I already bound to the surface. So we have an adsorption factor in the front, Ka, and a desorption rate, Kd, at the back. So this is also a kinetic adsorption model. This Langmuir, multi-component Langmuir model still makes a lot of assumption, and the main one being that each molecule is only binding to one side and there's no interaction between the bound molecules. However, this is in many cases not complex enough to describe what is actually happening on the surface. And this is why we're going to look at the additional adsorption model, mainly the steric mass action model, or also in this case, again, a multi-component steric mass action model. Steric mass action is mostly or commonly used for protein ion exchange chromatography because this model also captures the competition of our proteins with the counter ions, so the salts that we are using to elute or to regenerate our columns. This model takes into account charge effects. This means that proteins cannot only interact with one surface binding spot, but with multiple. This is also visualized in the graphic on the bottom right. You can see that these proteins interact with multiple binding spots at the same time. And also this model takes into account steric shielding. So this means that proteins can, with their size, right, and their form, block or shield multiple interaction sites. This is as well visualized again in the bottom. This protein is taking up two binding spots and also with its geometry is limiting other binding spots from being interacted with, right? So in this case, the three binding spots below the protein are blocked by the protein and can therefore not be interacted with by other proteins. We can look at the equation on the bottom left. We again have the change in the concentration on the stationary phase over the time, depending on the adsorption rate of our molecules and the desorption rate of our molecules. However, we also have here, not as on the slide before, um, the Q max, but we have this Q0, and this Q0 is defined also by the shielding of the bound species and the chart of the bound species, right? So this is just taking into account that bound molecules might take away more than a singular binding spot. Okay, we have now looked at different adsorption models, 3 in the name. However, this is just the beginning, right? There are many, many more adsorption models. Cadet, the software we are using for chromatography modeling alone, has over 25 different models included, and there are many, many more in literature. There are different adsorption models for hydrophobic interaction chromatography. We have models for size exclusion chromatography. We have models for affinity chromatography. As you can see, the list goes on. Multi-component adsorption models, just to give you a general idea that there is no limit really to what you can do in an adsorption model. Okay, as a last few points, I want to talk about what we need to know to build our own mechanistic chromatography models. Also, when we in the next screen guys are going to be looking into mechanistic models, what do we need to know about our system to actually build a mechanistic model? I color coded some of these parameters depending on how easy they are to determine. Red being more complicated than green. So what is quite easy to know, but what we have to know for our model is the column geometry. So what's the length of our column, what's the diameter of our column, and then we also need to know what is the particle, what is the porosity of our column, how much stationary phase is inside our column. We need the flow rate and the operating conditions. So we need to know what temperature is the system operating under, what is the flow rate. But these are easy factors that we are also controlling. So we know our inputs. Then next we have the particle and porosity information. This is most of the time something that you maybe get from your supplier of your material. They will tell you information about what is the porosity of the particles, what is the binding capacity of the particles, what is the radius or the diameter of the particles of the beads. Then we need obviously to know the dispersion and the mass transfer parameters, and these can be either, if you are looking at quite well-studied molecules, be derived from literature. Oftentimes, however, you have to determine these yourself with experiments or with earlier model stages. And then I would say the most complex parameters are the adsorption parameters and then the calibration and the validation of your data. So adsorption parameters are the adsorption rates, K adsorption, K desorption, the maximum binding capacity, stuff like the charge of your molecules, the shielding factor. These are all parameters that are quite difficult to determine, or at least you have to perform experiments and maybe also use models to determine these parameters already. As I said, some parameters are easily determinable, others might be provided by suppliers of your material or can be found in literature, and some have to be determined by experiments. Typical experiments that we therefore have to perform for chromatography are pulse injection experiments with acetone and blue-dextrain. Maybe you've already done these in a practicum or in a seminar. These are done to determine porosities of your system. Then we need to perform breakthrough curves or elution experiments with our target proteins or target molecules to get a good estimate to build a model on how to determine the adsorption parameters for these systems. So we have a short summary here at the end of what are the important key takeaways from the mechanistic modeling for chromatography. First, that chromatography is a fundamentally coupled coupled system. So we have a coupled transport and adsorption process that we can well describe with different independent model systems. We have convection, dispersion, mass transfer, and absorption are all important for the separation behavior. And we have model equations that directly represent the physical progress happening inside our column. We have different model classes and they have different trade-offs. Some models that we have seen are much easier, but they make strong assumptions about some of the effects happening in columns, while others are much more complex and take into account each effect in detail. The model hierarchy goes from the equilibrium dispersive model, which is the simplest and most straightforward, over the lump rate models to the general rate model, which is taking account everything in the transportation model. The key distinction between the models is therefore how the transportation limitations are treated or resolved. And then when talking about adsorption models, these models are important for the selectivity, the saturation, and the separation effects that are actually happening. So your model will not work without adsorption models. And then lastly, maybe more complex models are only really useful if we have enough data to parameterize them, right? As I said, the generate model takes into account every little step of the way of the separation. If you have no way or no experimental data to determine all these parameters that you need, then this model will never be able to represent your chromatography process successfully. So again, as already talked about in the basic introduction to modeling, the effective model selection really depends on the objective. What do you want to achieve with your process? How accurate does the model have to be? And what amount of data or what data do I have? All right, with this acquired knowledge, I invite you all to also watch the third screencast in which I'm gonna give a short introduction into Cadet. And we're gonna look at how modeling is actually done in the field.